Good morning, students. We have already covered analysis of series RLC circuit in our previous lecture. So now we are going to see resonance in series RLC circuit. What is resonance? Resonance is a phenomena when reactance of the inductor equals to the reactance of the capacitor. Means when XL equals to XC. What will happen when XL equals to XC? In a series RLC circuit, the impedance is given by Z equals to R plus J XL minus XC. So if XL and XC cancel out each others, the only impedance left is a resistive impedance. So at resistive impedance, the applied voltage is in phase with the current flowing in the circuit. So the circuit will behave as a pure resistive circuit. That means a series RLC circuit at resonance condition will behave as a pure resistive circuit. So this phenomena is called as resonance. This occurs at a particular given frequency, which is called as the resonant frequency. Now here we have a circuit where a series RLC circuit, to which we are giving an AC voltage Vm sin omega t and some current I of t is flowing through it. So what will happen in this circuit? There are two energy storing devices. One is inductor, the other one is capacitor. Inductor will store energy in the form of magnetic field, that is energy equals to half Li square, and capacitor will store energy in the form of electrostatic field, that is energy equals to half Cv square. Now what will happen when the capacitor discharges? Inductor builds up its magnetic field, and when the magnetic field of the inductor collapses, capacitor gets charged. So the oscillation occurs between this electrostatic field and magnetic field, and this process continues. So when resonance occurs, the resonance occurs at a specific frequency when the inductive reactance equals to the capacitive reactance, and this frequency is called the resonant frequency. And at resonance, the applied voltage is in phase with the current of the circuit. Means at resonance, the series RLC circuit will behave as a pure resistive circuit. Now let further analyze it. Inductive reactance XL is given as XL equals to omega L, where omega is the angular frequency given by omega equals to 2 pi f. So XL equals to 2 pi fl. That implies that XL is directly proportional to the frequency. So if we plot the graph between XL and frequency, we have taken XL in the y-axis and frequency in the x-axis. So we'll get a linear curve as XL is directly proportional to frequency. Now coming to capacitive reactance. Capacitive reactance Xc equals to 1 upon omega c equals to 1 upon 2 pi fc. This clearly means that Xc is inversely proportional to the frequency. So if we plot a curve between Xc and frequency, then we will get a rectangular hyperbola as Xc is inversely proportional to frequency. Now merging both the curves, we'll get a curve like this. In y-axis we have plotted XL and XC, and in x-axis we have plotted frequency. So the point where both the curve are meeting, that point is where the inductive reactance equals to the capacitive reactance, and that frequency is denoted as Fr, which is the resonant frequency. For frequency less than the resonant frequency, clearly from the graph we can see that Xc is greater than XL. So the series RLC circuit behaves as series RC circuit, means it will show capacitive effect. And for frequency greater than the resonant frequency, clearly XL is greater than the Xc, means the circuit will behave as inductive circuit. So same points have been mentioned here. Now if we need to find the resonant frequency, so what is happening at resonant? XL is equals to XC, that is omega RL equals to omega RC. So if we derive that, we come into the point that frequency equals to 1 upon 2 pi under root LC in terms of hertz, and angular frequency equals to 1 upon under root LC. Angular frequency unit is radian per second. Now we need to plot impedance versus frequency during series resonance. So impedance is given for a series RLC circuit, it is given as R plus J XL minus XC. This is a wave sign. This means that if XL is greater than XC, then we are going to do XL minus XC, and if XC is greater than XL, then we are going to do XC minus XL. So magnitude of impedance is also shown here. What is happening at resonance? At resonance, Z is only equals to R because XL and XC cancel out each other. So if we plot the impedance versus frequency graph, we will get a parabola like of curve, and the minimum frequency and at resonant frequency the impedance is minimum, that is Z equals to R. Now if we are going to plot current versus frequency during resonance, then in AC circuit voltage is equals to current into impedance. So current is inversely proportional to impedance. So current will be maximum at resonance. So we will get a curve like this. If you see the current versus frequency graph, we will see the current is maximum at resonant frequency, and we get a bell shaped curve for this. Now if we plot phase angle versus frequency, we have already seen for the frequency lower than the resonant frequency, the circuit behaves as a capacitive circuit, that is Xc is greater than XL. So for capacitive circuit, phase angle is negative and the maximum negative phase angle is minus 90 degree, a pure capacitor behavior. And similarly for frequency greater than the resonant frequency, XL is greater than XC, so we will get a positive phase angle, and the maximum positive phase angle will be 90 degree for a pure inductor. And at frequency equals to resonant frequency, the phase angle is 0 degree, that is we get a pure resistive circuit. So we need to summarize what happens at resonance in a series RLC circuit. So impedance is minimum, that is Z equals to R. As impedance is minimum, current is maximum at that point. The phase angle is 0 degrees. So if we calculate the power factor, then cos of 0 degree equals to 1. So we get unity power factor, and we can calculate frequency in terms of hertz and in terms of radian per second. Now coming to bandwidth. What is bandwidth? Bandwidth is the difference between lower cutoff frequency and upper cutoff frequency. And this cutoff frequency we calculate at a current that is 0.707 times of maximum current, which is the RMS value of current. This current corresponds to half of the maximum power. So mathematically, bandwidth equals to upper cutoff frequency minus lower cutoff frequency. In terms of radian per second, in terms of angular frequency, it will be bandwidth will be equals to WH minus WL. So for the series RLC circuit, we will calculate the value of WH and WL, and we will come to this conclusion. We will get WH and WL, and then we can definitely find the bandwidth. So the resultant bandwidth what we got is R upon 2 pi L. And also from the previous figure, we can mention that FL equals to resonant frequency minus bandwidth by 2, and FH equals to resonant frequency plus bandwidth by 2. Now coming to quality factor. What is quality factor? It is the measure of voltage magnification, or it is the measure of sharpness of the current curve. So Q can be simply given as the voltage across the inductor divided by voltage across the resistance, or voltage across the capacitor divided by the voltage across resistance. So just we have calculated the quality factor in terms of L and R, in terms of bandwidth, and quality factor in terms of RL and C. So if we know the value of resistance, inductor and capacitor of the circuit, quality factor can be determined. Thank you, students.